Section 1 of Chapter 7 is basic trig identities. An identity is a statement of equality between two expressions that is true for all values of the variables for which the expressions are defined. So what it's saying is when we are solving identities, okay, we want to make both sides of the equal sign true. And a lot of times they'll say prove that this identity is true. So like one example they might give is prove that for every angle, um, sine over cosine is tangent of theta or something like that. And we'll be able to use, what we're going to do is we're going to test our algebra a little bit and our knowledge of trig functions, and we're going to manipulate each side in order to get it equal the same thing, okay? And right now, obviously, I'm not going to solve this because we don't know our trig functions yet, and that's what we're going to go through right now. Okay, a trig identity is just identity with trig expressions, so that's what we're using. This would be like an identity, prove that this is true. This is true. We'll get to that later, though. So let's talk about some identities that we can have. Reciprocal identities, we already know this. These identities hold true except for those that make the denominator 0. We already know that sine and cosecant are reciprocals of each other. We've already talked about that, and cosine is reciprocal. Its reciprocal is 1 over secant. We've talked about all that stuff already before. Okay, so that's nothing too new for us. It's just putting it out there for things for us to use. So now it says if tangent of A is 8/10, find cotangent of A. Well, that's pretty easy. We know they're reciprocals of each other. We know that if we say, okay, well then the cotangent of A has got to be the reciprocal, so it's got to be 1 all over 0.08. Or if we looked at it, 8/10 as a fraction would be 8/10, right? So if it's reciprocal, so cotangent would be 10 over 8, right? And we could simplify that as well to be 5/4. So that's all it's saying right there. That's all we talked about. We knew that already. We've talked about that already. That shouldn't be anything new for you. One thing that is probably new for you, though, and I'll explain here why. This identity says here sine over cosine is tangent, is equal to tangent, and vice versa. Tangent is equal to sine over cosine. A lot of times this this right here identity will help us in solving quite a few equations. Same thing with cotangent. All right, it's just reciprocal of that, cosine A over sine A. Okay, and I'll show you why here. Let me draw a unit circle. And here's where they come up with this. Say I have an angle here, and we want to know this angle, and we're just going to call it theta or A or whatever. Okay, so what it's saying that the sine of A, the sine value over the cosine value is equal to tangent. Well, we've talked about how to read our charts. You know how our charts give us ordered pairs like 1/2 and square root of 3 over 2 or something like that, right? We've talked about how the x values is the cosine value, right? And the y values is the sine value. So if you look at this angle right here, if I want to know the tangent of it, I'm taking the sine value and I'm dividing it by the cosine value right here. Tangent is opposite all over adjacent. All right. So that's where we get that tangent is equal to the sine value divided by the cosine value. So let's just make this triangle that I drew here a 30, 60, 90 triangle. All right. And we'll give it a reference angle of 30 degrees. So here's 30 degrees. We know our 30, 60, 90 is 1, square root of 3 down here, and 2 up top. So the sine of 30 degrees is 1/2, right? Opposite all over hypotenuse. And the cosine of 30 degrees is the square root of 3 over 2. The tangent of 30 degrees would be opposite all over adjacent, which would be 1 all over the square root of 3. So tangent of 30 is 1 all over the square root of 3 or square root of 3 over 3. We've talked about that too. Okay, so what I'm going to show you and what I'm going to prove here is that if we write the sine value over the cosine value, we're going to get its tangent value. All right, so here we go. The sine's value is 1/2 divided by the cosine value, which is square root of 3 all over 2. If we think about it this way, this is dividing fractions, and a lot of you guys are a lot more comfortable if I write it like this: 1/2 divided by the square root of 3 over 2. We know when we divide fractions, we save this fraction, we change this sign to multiplication, and we flip this fraction, right? So I'm going to flip it to 2 all over the square root of 3. Now when I multiply, I can look diagonal before I multiply, and I can cross out. I can cross out these 2's, and now all of a sudden now I have 1 all over the square root of 3. Isn't that the same thing that we already came up with the tangent of 30? So I'm just proving to you why this identity holds true. I just showed you one example. I guess I didn't prove to you that it holds true all the time, but I'm showing you one example of where this came from. All right, it's saying that the sine value over the cosine value is always going to be equal to the tangent value. And the same thing if I were to do the cosine value over the sine value of an angle, it'd be equal to the cotangent value. All right. So I'll just showing you that that's true. So here are 2 identities for us. In that same sense, these over here are just manipulating this equation. So it's saying at the same time, sine can be equal. We can substitute, instead of writing sine in the equation, we could substitute cosine A times tangent of A. And all it did was it said, okay, if I want to multiply both sides by the cosine of A, so these cancel out. And that's a legal algebra step. So now all it did is wrote sine A equals cosine A times tangent A. That's all it did over here. So what we can use these identities for is if they give us a tangent, we know that instead of tangent, we could write sine over cosine. Maybe that helps cancel some things out. Maybe it helps simplify our equation. So that's what we're doing there. And in the same sense here, cosine, instead of, if we see a cosine, we can substitute in sine times cotangent of A if we want to. All right? And that's just saying that they wanted to multiply by sine on each side. These are all the same then. Okay? All right. Moving on. We also have some Pythagorean identities. All right, it's saying that the sine value squared plus the cosine value squared should equal 1. And again, I can show you that on our unit circle, and it should make sense to you. We know that our unit circle has a radius of 1 degree, right? So every time it has a radius of 1. So it's saying our sine value, which is our y value, our sine value squared, they're all right triangles, so we can use the Pythagorean theorem. Our sine value is a y value, and our cosine value is the x value. We're saying that for this, our sine squared plus our cosine squared should equal our hypotenuse, which is always 1. It's always going to the end of the unit circle, which has a radius of 1. So sine squared plus cosine squared equals 1. And by the way, helpful tip here, when it's written sine squared of A like that, that means the same thing as sine of A squared. It means the same thing. Don't ask me why they denote it the other way. I'm not sure. As far, maybe they're just saving time of writing parentheses. I don't know. But this is the same thing as that. All right? That's a common where people get tripped up too. Okay? And again, there's other, by manipulating these equations, we all get that, okay, we have these other Pythagorean identities. All right, the tangent value squared plus 1 equals the secant value squared. 1 plus the cotangent squared A equals cosecant squared A. So why are we finding and writing these identities down is because anywhere I see maybe sine squared plus cosine squared, I know like instead of having this in our equation, I can replace that with 1. I know that sine squared plus cosine squared equals 1. So I'm going to substitute in 1 for that. In the same sense, if we ever come across the tangent squared plus 1 equals secant squared, well, instead of tangent squared plus 1, I can plug in secant squared, or vice versa. Maybe I see secant squared, I can plug in tangent squared plus 1. And same thing over here. All right, so all these identities are giving us options that we can manipulate equations. So we're going to change stuff. All right, so here we are. Here's just an example of using the Pythagorean identities. Here they give us tangent of A is 2/5. They want us to find cosine. All right, well, first of all, let's look up here. Where are we dealing with tangent? Well, these two deal with tangent, right? Well, if I find its secant value, as long as then I can just find its reciprocal, then all of a sudden I have its cosine value, right? So I know its tangent value, so I'm just going to say, all right, well, 2/5 squared plus 1 equals secant squared, right? So I square this thing out and I get 4 all over 25 plus 1 equals secant squared. Add these two terms together, it'd be 25 over 25. I'd have 29 over 25 equals secant squared. I want to get secant by itself, because if I know secant, then I can get my cosine. I want to take the square root of both sides. So I have the square root of 29 all over 5. If you remember that anytime you take the square root of a fraction, it's the square root of the top divided by the square root of the bottom. And so that's going to be secant then, because I took the square root. It's just going to be secant. If I know the secant value using our identity from up above, if I know secant, then I know cosine, because they're just reciprocals of each other. So it would be 5 all over the square root of 29, which we know we can rewrite 5 over the square root of 29 without a radical on the bottom. If we multiply by the square root of 29 over the square root of 29, we'd get 5 square root of 29 all over 29. So there you go, like that. Pretty simple. We're just using our identity. Here, in this case, they give us a secant value, and they want us to find its cosine value. Well, that's pretty easy, right? I'm not sure we need to use a Pythagorean identity for that. If we know its secant value, we can just flip it, and we find our cosecant value. That's easy enough. So cosine is just 4/3. Okay. This one, however, if we already have its cosine value, and we want to find its cosecant value, we know that cosecant is the reciprocal of sine. So if we find its sine value, we'll be able to find its, if we find its cosecant value, we'll be able to find its sine value. Easy enough. All right. So we know that this identity right here is going to help us out. Sine squared plus cosine squared equals 1. I know my cosine. I don't know sine. Sine squared of a plus my cosine value, which is 3/5 squared, equals 1. Okay, well, sine squared a equals 9/20, or sorry, plus, my bad, plus 9/25 equals 1. I'm going to subtract 9/25 from the other side. So I get sine squared a equals, this would be, this 1 right here would be 25 over 25 as a fraction with the common denominator right here, right? Subtract the top minus the top, I get 16/25. I need to get sine by itself, so I'm going to take the square root of both sides. So I get sine of a equals 4/5. So if I know that my sine of a, that means I know my cosine a, because those reciprocal identities we talked about earlier. If I know the sine of a, I know cosecant of a. All we need to do is flip it. So cosecant of a then equals 5/4. Okay. That's all I have for you in this video. I went a little longer than I wanted to, but I want to make sure you guys understand this stuff and how to use identities. And as very, very basic right now, we'll get more into it as this chapter continues. Hope this helps. See you in class.